And the next speaker is Franko from the ZEUS facility, and he'll be talking about the data management within his research infrastructure. Welcome, Franko. Please
Thank
share.
you very much. So sorry.
And
We just have a little bit of feedback.
Yeah, it's co-presented also with Zhang. Welcome, Zhang.
All right. Good. So I would like to, do you have the feedback as well as I hear it, or?
I don't hear it. It sounds good.
Perfect. So then I'll just keep going. I just, as you said, I wanted to mention Qing, our data scientist, because we're going to share that talk here. And today we are going to show you a little bit how we extract the data within our ZEUS laser facility. So ZEUS is an acronym. And if you wouldn't mind to move to the next slide, please. ZEUS is an acronym that I'm going to explain here in a second about the signature experiment, and it stands for Zetawatt-Equivalent Ultrashort Pulse Laser System. And that's lab is a external user facility where institutions submit proposals to an external independent panel, and based on scientific merit are awarded laser time for their experiments. The typical experiments that we here perform are in the aspect of what we call laser wake field accelerations. That's the acceleration of either ionized or charged particles with photons. And our signature experiment here stands for a Zetawatt equivalent, which means our laboratory is not able to generate a Zetawatt equivalent laser pulse. Our pulse has a power of 10 to the 15th, which is a petawatt, or in the petawatt range. But however, we have a colliding experiment where in multi-GeV electron beam collides with the high intensity laser beam. And in the rest frame of the electron basically experiences it as a Zetawatt experiment. So the next slide, please. What this means in terms of electric field strength, the electron positron pair generation has a Schwinger limit, which is 10 to the 18th. And we are, with our experiment at laboratory experiments, about the current record is 10 to the 15th. So we are attempting to break that record and move into that regime. If you wouldn't mind to go to the next experiment, next slide. I don't want to go too much in the scientific side, because what we are really about here is how we are actually collecting the data. And I have a very short video that probably explains better in terms of what we do, but also then how it pertains to the data collection. So here, just a brief overview of our lab. Since the video is we have a fly-through video, is going rather quickly through this. So we're collecting in our laboratory two main data sets. The number one data set is anything related to our laser. That means as the pulse moves through our amplification chains, it starts in the red area. We measure throughout the system, spectral, temporal measurements. We measure energy and collect that data then in a laser shot log that then is made available to the experimenters, because they collect in the blue areas experimental data. And these two data sets is what we then collect in the form of an experiment and provide to the laser. I just wanted to show what you see here in the video. It will probably make a lot more sense. The red area is where the pulse progresses through our amplification chains, and then it moves through into the vacuum system. We have about 39 metric meters of vacuum that then gets distributed through to 3 different target areas. The video with the signature experiment is in our target area 1. And I'd like to walk you through that one. With that, maybe we just can start the video. So what you will see is a laser coming from our commercial front end. Oh, that's maybe the wrong video. Okay, so here comes the laser pulse as it comes out of the commercial end. So it is at this time approximately 40 millimeters in diameters and a nanometer in length. And then it grows as it progresses through these amplification chains. As you see here to the left, the pump lasers, it grows in size to 140 millimeters. At that point, then we take a laser beam, split the beam. So we have a time measurements as well as energy measurements that we have to consider. Then it goes in here into these vacuum chambers, into our vacuum compressors. At that time, we can only measure in vacuum. And then from there, it delivers the laser pulse into the target area that is heavily shielded because of radiation. So we have in this regard also radiation measurements to contend with. And that here is our target area 2, where we shoot at solid targets as well as gas targets. So we have different type of measurements that we need to take. And 1 second. Next slide. Exactly. So we have also, in addition to the target area 1, a target area 3, and that is gives you more high repetition rate at a lower energy level, but a higher repetition rate, also in form of laser wake field acceleration. So with that, I'd like to hand it over actually to Qing, because all throughout here, the measurements that we are taking is through multiple stations and cameras and spectrometers that Qing then handles and disperses.
Yeah. Do you need to mute and turn off your volume? Yeah. Yeah, so I'm Qing. I'm going to continue to talk about the data management in ZEUS. So here is the general data lifecycle from data acquisition to dissemination in ZEUS. So all the devices we have are in the local network, and we run the data acquisition software in the workstations, and we can save the data either to a local SSD or to a local network attached storage, or even directly to a mapped cloud storage. We have 2 cloud storage, and both are located in the advanced research computing of the University of Michigan. So one of them is called DataDen. It is for archived purpose. The other is called Turbo and can be direct mapped to a laboratory computer, or it can also be accessed by Globus, and it is connected to a supercomputer in a university. So DataDen has some limitations, but its cost is much lower than Turbo. So if the data were saved, I mean, the user data was saved locally in those network, we will then copy the data to the cloud storages. After that, the users can get the data from both storage servers by Globus. So to summary, we have a few storages for different purpose. Online, we have online storage, we have offline storages, we have short-term and long-term storages. In the next few slides, I will provide more details on how we share the data with users. So let's start from the very beginning. Usually since we are user facility, so after user experiment proposal is approved by us, so there will be a web page for the experimental details where the group members will be imported from the submitted proposals. The PI will revise the experimental list, and all the listed group members will receive notification emails asking them to submit their Globus ID if they would like to access the data. So all these are done weeks before the experiment start. And since we already have the user's Globus ID in our database, we can create the data directory for the for these users and give them access permissions. The operations can be done with just one click in the web page. So it will give all the users the access permission if their Globus ID are in our database. In this case, so the users are able to access the data directory before the experiment starts, and they can test their data analysis code with the designated directory. For the users to access the data, we have a web page on ZEUS portal. So ZEUS portal is a website for us to manage user information, proposal, experiment, calendar, research data, etc. So the users can view their participated experiments, and there are corresponding links to the data. So click the links, either of those two links will redirect them to the Globus web page. We use Globus to share the data with the users. Globus is a fast, secure, reliable way to move data. It's especially good at transfer large amount of data. The procedure here is quite easy. So the users select the source directory, which is basically our data repository they already have access to, and they select the destination directory, which can be either their own computers or any other storages they have access to. So click start will start the transfer. And if any errors occur during the data transfer process, it will keep trying to reconnect until the download is resumed. Globus also support further programming development, and it supports Python and also other programming languages. This means the users can do some like real-time data analysis, even if they are offsite, and also they can adjust experiment plan based on some preliminary result. Here is the real test I did to verify the data transfer speed. So the average transfer speed over 1 minute can go up to 80 megabytes per second in real conditions. And this is most likely limited to my local bandwidth because I only have like 1 gigabit per second bandwidth or my hardware writing speed. This means the speed of data servers are quite good, and the data transfer speed to the users, usually they are only limited by the user side instead of our side. This part, I'm going to talk about the data acquisition to the first storage architecture. Starting from last year, we began to adopt Tango control as the main system control and data acquisition framework. So Tango is a free open source device-oriented control toolkit. It can control any kind of hardware or software and build the SCADA system. It is operating system independent, and it supports C++, Java, and Python for all of its components, like its client, its servers, the database. Compared to Epic, so which many of you might be familiar with, Tango supports Python programming for device servers, and it is support OOP, so it's better at code reuse and encapsulation. We have an open repository and Git. So here I'm going to give an example of the data acquisition GUI developed by us basically using Tango control, Torus, and Tinter. So all the communications behind the GUI in the back end are achieved by Tango. The screenshot in the left is a startup interface, which is written by Python Tinter. Users can select the device from a device list. They can see all of our laboratory device, and when they click device GUI, it will automatically generate a Torus GUI, which combines the selected devices. The Torus GUI layout can be further customized. we can stack or tile or hide or grid all these panels. The layout settings can also be saved, and then the settings can be easily loaded next time when we restart the GUI. We have some pre-coded data acquisition loop with customized options, and the users can select devices to scan with. For example, like they want to scan motors, delay generators, or other devices. Also, I/O bound operations, for example, data transfer and data saving, are mostly made asynchronous to make the data visualization more real time, and to support higher repetition data acquisition. Because in one of our target area, the short frequency is very fast. As you can see here, a shot is claimed completed, and the conditions was set for next shot actually before the shot data is actually saved. So the time gap here is relatively small. It's like less than 1 second, but this is only because I just use one low resolution camera in the loop. In our real experiment, when we have like 10 high resolution cameras, we can save tens of seconds for each shot. Another advantage of using Tango is the convenience and its user-friendly syntax. So by mouse over the labels in the GUI, the users know how to access the properties. For example, here we mouse over the exposure label of a camera. From the tooltip, we can know the property is named exposure and it belongs to a certain device. Then we can read it or write to it by just 2 or 3 lines of code from any computers in the lab. So this simple syntax facilitates user coding for customized procedures, especially during the experiments. For the data format, there's actually not too much to say. Currently, we are using individual files for from each instrument, and also like a metadata file for them for the shot. In the future, we could like maybe adopt HDF5 data format or Nexus data standard. So all those I just talked about are basically the current data management architecture in ZEUS. Problem solved along the way and lesson learned. We have many problems and difficulties in like recent 2 or 3 years. So 2 years ago, we didn't have our own storage server. So we basically just used Dropbox to share the data with the users. But now we host our own medium-term and long-term cloud storage servers. And one of them is connected to supercomputers. We didn't have the data acquisition GUI, so we basically just run script from the terminal, and now we have like flexible data acquisition GUI. We didn't have like user information database. Now we have a website which hosts all those user-related informations. We solved a lot of problems on the way, but I would like to share my own experience and lesson learned here. So first is like, unless you have a large development team, you should most likely like utilize existing architecture. So for us, the University of Michigan has a Department of Advanced Research Computing. So storage and computing resources are available with relatively low cost, and they are well maintained and are supported by professional engineers. Second is we should always development software based on active maintained library. So we use Globus to share large data. It's free to common users and is subscribed by many institutions. So it's stable, powerful, and efficient. Also, we use Tango Control and Torus GUI to build our customized data acquisition GUI. Yet we still have some challenges currently and also in the future, I believe. So for example, we have too many cameras in the lab. So however, usually we just use one workstation to receive all the data from those cameras and like display or visualize them. The bottleneck would be the bandwidth, which may limit our shot frequency in the future. Also, we still need to improve the data acquisition automation. The third is we currently don't have any machine learning in the system control, so except some building algorithms from like commercial devices like deformer mirror. Another challenge there is the open data policy. Of course, usually the user, they don't have interest in sharing data with others, but NSF hope we can make more use of the data and make them public. So also this requires better documentation. We have plans to make a user agreement on open data policy, and we are working on the language. So if any of you have the experience or maybe have a template to share, we'll appreciate. So at last, we are actually calling for proposals for fiscal year 26. We had a town hall meeting last November, and the video is available online. The proposal submission portal is also open, and we welcome any proposals, and we appreciate if you can share with your colleagues. That's our ZEUS team. Yeah, thanks.
Great. Thank you so much, Franko and Qing. And so the floor is open for questions.